Rick, that's you. You're the driver?
Okay. Well, thanks for coming in again. Appreciate your attendance. And so we talked about this morning, just kind of a quick recap of what our basic air handler looks like. And again, air handlers devices used to condition air and move that air throughout the space. So units like we build out in the shop, considering they're a horizontal unit, are going to be a rooftop model with kind of this arrangement of components in it. And I wanted to point out that in this case, we showed an evaporator coil, whether a DX or maybe a chill water, but also we built some units, we have evaporative media for the cooling means as well. So that can be another way of putting some cooling into a space, not an office space per se, but we can cool a space with evaporation. Just want to bring that up so everyone's aware of it, some of the options we can do. And again, we're talking about the blower. It's the heart of the air handler because again, it's like the heart of our body. It's pumping the fluid, air it is, the fluid throughout the system. It's just a continuous circle that it runs. So we turn air through the components, filter, cooling, pick it up here, option depending on the application, back to the space, and keeps doing this over and over. But again, that's the pump, just like our heart. So that's the heart of the air handler. Now, we use basic types of fans in the units that we typically build. The typical fan, the air enters it to a parallel with the motor shaft. So air comes in this way and it's spun around and discharges out front. That's the centrifugal fan. Then and we blow it out as a centrifugal force. So the air is forced to turn. It comes in one direction, goes out the other direction. Common types that you see in HVAC. By the most common, just because they're the most economical type fan, relatively simple to stamp out the blades, put them together. And they're very efficient for low static pressure applications. You start getting high static pressures because of ductwork, components, whatever it might be, they start having some shortcomings and they can't keep up with the pressure you need. Backward inclined, the blade, it runs backwards, counterintuitive. The blade, instead of slapping the air going like this, the blade's like this rotating. But you get higher efficiency out of them. You also get more noise because they run about twice as fast as a normal fan does. But they are very good when you start getting into higher static pressures, whether it's filters or whatever you might have, but you have to put up with that pressure. A lot of ductwork, for example. And then sometimes a plenum fan is used. I heard some people mention in the earlier session, the Matto unit. Well, this is what's being used in the Matto unit, is the plenum fan. There's no housing on it. It's just an open fan and it pressurizes the whole plenum and the air moves accordingly. You don't have a blower with a housing that you direct the air. It just pressurizes it, takes the path of least resistance out of the area. So here's an example of the forward curve fan. Air comes in parallel with the motor shaft and or blower shaft. Spun around in here, high velocity opening up the front. So you can see how it comes in one direction and turns. This particular one, and we commonly use it here for, I think, most of our applications, it's called a double width, double inlet. So you see it's basically two halves of the wheel. Air enters from both sides. Some of the smaller residential units might be a single width, single inlet. You only have the air enter from one side and come out just at a smaller capacity. But you can see again how they get that shape, and then this venturi is curved to help smooth the air in, so it's not quite so turbulent when it comes in there. It's more efficient that way with a rounded edge. You get a raw edge, and the air just comes in and starts swirling like this. Like this way, we're directing the airflow for a better performance.
And those blades are curved, so they kind of cut the air as it grabs it as the fan turns.
Okay.
And the negative thing of that, though, if you get in a dirty atmosphere, those blades load up with dirt.
Yeah.
dust, dirt, whatever. And you have to go in there every once in a while and almost like a wire brush and scrape all that stuff off to get your performance back again.
The toothbrush.
So, but yes, there's just, as we said, they're cupped and they just scoop the air and push it out. Here's the DI wheel we talked about, and see, instead of the cup wheels, it's leaning backwards. To me, it's counterintuitive how it works, but you can do that air. Again, they run about twice the RPM. So if they increase the efficiency, that's the good news. But you also have to be aware of the noise they might generate. They are a noisy fan. But where the forward curve might run at a 400 RPM for certain applications, these need to run 800 RPM. And next is the plenum fan you talked about. Again, it's the backward inclined process. So it's a high frequency wheel. In this particular case, it's direct drive, so you don't have any loss with the belt drive. And you're pressurizing the whole chamber, and then the air just moves again through the path of least resistance. And you, in the room, remember the units were the other buildings were the Amazon units. They used a number of these. They had a whole wall of these in one big chamber.
Excuse me.
And wall by concept, some of them used for that. But the Matter uses up to 8 of them in their design.
Yeah.
So now we're going to start talking a little bit more on the cooling side. So, as we said before, you get a refrigeration system. The evaporator coils in our unit, but remote of this and provided by other people is a condensing unit. And that's what gets the circuit going in the refrigeration cycle that pumps the air through, or not the gas, air, but the gas through here and gets. So if you look at that though, back up to it, the condenser fan up on top, that's what pulls the air through the condenser coil and exhausts it outside in the space, or not the space, but out in the atmosphere. Well, this is what a condenser fan looks like. It's an axial fan. A prop fan, as it's commonly known, but the axial fan, it causes the gas to flow in the axial direction parallel with the shaft. So we don't change direction. We're looking online at it. So the air comes in through the bottom, air spins it and blows out the same direction. Not turn the air like the typical fans do. So this is a small one like you see on a condensing unit. This is a larger one like we use in our IFP air turnover units. It's just a larger version of the same type of axial fan. So again, the typical fans that we use in Dallas are centrifugal, and there's 3 variations of centrifugal or axial. Axial fans, we said before, they move a lot of air, but they can't handle static. So you start getting any static system, you don't see these different stuff working very seldom because of the limitations. Now we're going to jump into some decorative cooling. And again, we're going to do a refresher course on some of the terms. The dry bulb temperature is the temperature you take on the ordinary thermometer. You have a thermometer in your yard you're feeding, or you hear the weatherman talking. That's a dry bulb. The wet bulb temperature evaporates when the air is blown over it. So as we pointed out, usually done with a sling psychrometer. And that's really a thing of the past. Doug might have an antique one in his office.
I do.
See? But you have 2 thermometers on it. You put a wet sock in one of them with distilled water so you don't get minerals on there. And you have a dry one. You spin it. One stays constant as the dry bulb. The wet one lowers to the wet bulb temperature. And that's so you can find the temperatures of the 2.
Talking about the evaporative system, that's understandable. Thank you.
Relative humidity, that's the percent of moisture in the air compared to what it could possibly hold. So if you've got a 90%, as Doug was saying this morning, 90% or higher relative humidity, you're almost raining, or could be raining, because air is that moist, it can't hold any more moisture, it's gonna start getting rid of it. On the other hand, I use the example again of Phoenix, they're very dry. You don't even sweat in Phoenix because it's so dry that it just evaporates immediately. Wet bulb depression, that's the difference between a dry bulb and a wet bulb temperature. So just an example here, if a dry bulb was 100, a wet bulb is 70, your wet bulb depression, or the delta T we keep talking about, that delta T term, 100 minus 70 is a 30-degree differential. And then a spike chart, a psychrometric chart, I'll use the full term. That's just a graphical way to show some of the properties of air. And I know this isn't the most clear thing. Thank you. But because Xerox copy of a smaller spike chart so we can see that. And we'll go over some of the basics here in a couple minutes of what this can be a very complicated graphical information here. I'm sure that you could have a complete college course, semester at least, in engineering of all the things you could learn from this spike chart. We're going to talk about three basic things, keep it very simple for us, but just so you can appreciate what we can learn from it. In reality, in today's technology, this is all computerized. We just want to show you what we did it in the long term and what information is here. I'll get you copies of the big one that we can fit on the machine. So if you look at that now, you see across the bottom, it says dry bulb temperature. And dry bulb temperature on this graph is red, it's the vertical lines. So you see the numbers down there, and then you see the vertical line that you then can plot upwards or whatever we're gonna intersect with another term later. So that's the dry bulb. We're going to go into wet bulb, and they're the one like a diagonal, 45-degree diagonal. When they come in from the top, here is the temperature here, wet bulb, and then going down the graph there. Can anybody see the ones going down to the right?
Yes.
That's your wet bulb. And then the last term we're going to get into right now is the relative humidity. And that's the one that sweeps. There you go. I'll see someone pointing at it here. They start at the bottom real close together, then sweep up, and you see numbers on them about halfway up the chart. So that's the 3 point we're going to get into is the basic of a site chart. So with that being known, or I don't know whether you still have it anymore, but when I used to live here many years ago, this was in the paper every day. We had yesterday's diary in the weather section, and it would tell us the 24 hours the temperature and humidity was at every hour of the day. And then you can see that, say, 4 a.m., humidity is up to 59% in this case. So we really aren't worried about that much cooling at 4 a.m. But in the 4 o'clock time, when it's 104, humidity is dropping to 29%. What that drives us to say is with direct evap cooling, it works the best when you need it the most. You need that wet bulb depression to make it work the best. You don't have that much here, but how much do you really need? And at 4 a.m. or 4 p.m., when it's 104, you're less than 30% humidity. So how direct evaporation is, you have air coming in, hot air, whatever you want to call it. Air goes through it. But the water cools the air by converting the air sensible heat to latent heat. Dry bulb approaches wet bulb because wet bulb is going to go up as it picks up this moisture to it. That's why we got a higher wet bulb in. So again, you don't want to have a direct evap. It's just going to become a rainforest if you're circulating that. Going through one time and then blowing it out in the exhaust, they work great. You bring a lot of air into the building, cool it down, blow it out. We put all these evaps on the roof in here. Our resident then was Ed Graham. I remember him. We put him in there. It used to be a 100-degree day in Dallas. Before the end of the shift, it'd be about 115 degrees out in the shop at the end of the day. It got that warm out there before the day was done. We put all these evaps in, and we moved a lot of air. I mean, you'd knock your hat off your head when you went in the door blowing so much air out. On a 100-degree day, we kept it down to 85. The shop productivity went up 20%. Just because of the working conditions.
Yeah.
They were just, had to be dead on their feet by the end of the day. So that's what evap cooling can do. But again, we don't return it. It's one time through and we're out. But it's inexpensive too. You don't have any refrigeration system to worry about. So just pumping the air through.
The only thing you have to do is replace the evaporative media pad.
That's true. And then that's based,
That's a maintenance.
the major supplier for this, I know there's multiple suppliers now. These say this media would last 5 years. And generally, I think we found that would be very true. I've got a small one in my garage I use to cool me when I'm out in the shop. I've had it for 8, 9 years now. Should be replaced, but hasn't been replaced yet. It still does a good, decent job for it. On the other hand, our rep we had in Texas had to replace it every year. Their water was so bad out there with minerals. Every year they had to replace the media. So generally, you'll get around 5 years out of it. That's pretty good estimate. But that's a good point, Doug. That is the one thing you have to do.
Yeah. But there's no compressors or anything like that that cost energy dollars.
So what do we actually see from that now? What do we really pick up? Effectiveness of the cooling efficiency or saturation effectiveness. But the temperature drop across the media compared to wet bulb depression. So if the wet bulb depression is 30 in our example, and we drop the temperature 27 degrees, we had an efficiency of 90%. So you take your wet bulb depression, we figured out through the wet bulb or the site chart, we're going to get into an example. And then you see what you're actually discharging, and you can learn what your efficiency is. In this example, it's 90% because it was an easy number. But on our units, the velocities we're putting through one with 87 units. Nominal 90%, but the true 87 that we use for our calculations. So what we do now, the leaving air temperature, dry bulb temperature, minus static efficiency or saturation efficiency, I'm sorry, times outdoor minus dry bulb minus wet bulb or wet bulb depression, right? You take the static saturation efficiency, I'm sorry, times the depression. So here's a little example here. And we're going to go back to the chart here in a minute to show you. We're going to see the difference between a 6 a.m. and a 4 p.m. calculation. And you can try to follow along on that pie chart. I know it's a little bit harder to see. I went through a bigger one this morning just so we can talk about it. 6 a.m. it showed a temperature of 82.65. Well, I took 82 dry bulb, I went up to where I could estimate 65% relative humidity, which I know is kind of hard to do, where it's 50% between those two lines, but I came up with a wet bulb temperature of about 73 degrees. Now I think it comes into that chart. You can kind of see where I'm hitting those two lines and where it comes up. You have to look at this slide chart here.
Okay.
82 degrees on the bottom for dry bulb. Take a straight S, we get 65% on that curve. And 65%, where is 65%? I have 73 degrees I come up with. I had a vision slightly more accurate than you can read, but that's how I determined. So if you have the dry bulb and humidity, and the wet bulb, we're trying to say here. Anybody,
It's a 60.
we kind of follow, need a little assistance?
These are hard to read.
They are hard, I agree. Okay, so with that in mind, we'll fill in the formula now. At 82 degrees coming in, 73 wet bulbs with a 9-degree depression. 0.87 times 9 degrees is 7.83, almost 8 degrees. So 82 minus 8, you have a leaving air of 74 that you'd have at 6 a.m. Didn't cool it that much, but you dropped it a couple degrees at 6 a.m. in the morning. Now, let's take this 4 p.m. calculation. Now it's 104.29. So first, guess you come up with what number that's going to be.
104.
Dry bulb?
104 dry bulb,
Okay.
29.
About 100?
I got 77.
I got like.
Yeah, the smaller one that you're looking at is harder to read. Again, I've got the expanded.
Yeah.
I wanted to copy these, but they wouldn't fit on the machine, so. But you can kind of see how we're getting that now. So again, you have 2 points, you get the third one. So now we have a 27-degree difference from 104 down to 77. Cut it down 27 degrees for the wet bulb depression. So you take that formula in there. We're dropping at 23.49 degrees, leaving at 80 degrees. Coming in at 104, leaving at 80. That again stresses my point. Works the best when you need it the most. You didn't need that much cooling at 6 a.m. You sure needed it at 4. And that dropped at 23 degrees. Again, with no refrigeration. And you can understand now, although we had a lot of air moving, we had a lot of big units running. You can understand how we cut the shop temperature down that much in those.
And truthfully, at 6 a.m. with the amount of air you're moving, you probably didn't need the heat off.
No, you could probably turn the pump off during that time. I would agree. Yeah. So we improved the productivity enough that Ed Graham was gonna put it in the office too. At least he threatened to. So just want you to see that, that's what the directly evaporative cooling can do for you. So we can lower it from, again, on the hottest part of the day, lower it almost 25 degrees. Ross?
I'm still a little lost because I think I just may have to work through it. Maybe.
Can we go over it again?
We can. I'm open to that.
What? You don't understand the site chart, or what are we?
Well, I understand the chart. I'm not understanding the differential, I guess. the time versus the time of the day, how you getting the numbers?
Oh,
Yeah,
I got those numbers from our,
From the chart.
from those,
Mm-hmm.
okay, thank you.
so again, so if you hear the weatherman say that it's 104 and 29% humidity, if you look at this, you get a pretty good idea what the wet bulb temperature is, because they don't talk wet bulb in the weather stuff like we do.
Okay,
So, but you have that number and you have a side chart, you can determine it.
thank you.
I'm getting confused on, is the saturation efficiency the same as the relative humidity?
Now, relative humidity is what helps us determine the wet bulb. Saturation efficiency is the effectiveness of the cooler itself.
So how are we getting the saturation efficiency numbers?
That's what I gave you.
That's the calculation.
Oh, okay,
For the turbo cell, we're gonna use 0.87.
okay.
Does that make sense now?
Yeah, so we were using 87 to get,
Numbers I came up with.
okay.
Yes. And that's a broad statement. 87% is probably based on our maximum CFM. If you pick a lower CFM in the same box, it's gonna be approaching the 90 because you're gonna get better heat transfer at the lower velocities. But we stuck this as our highest number, worst case scenario, that's what we published. People feel so looking at the chart, will clarify what you need.
Yes, it did.
Okay.
Thank you.
Okay. So that's how we calculate the temperatures on a direct evap unit. Now let's talk about indirect evap. Indirect, the water will never touch the airstream. They're in contact with supply air, thus the indirect. And you have efficiencies now or effectiveness of 75%. That's what Aztec uses for effectiveness of their cooler. And when it's been proven out, we can't complain about it. So 75% effective versus 0.87. It's straight sensible cooling, but it does reduce wet bulb temperature. We'll show you in the slide chart here in a minute of how that works. Well, here's how the system works. You got a cooling tower that water pumps through, and we cool the water down through this. Just the same evap media that we use here as you do in the direct section. But if the water runs through there, it cools off. So then we pump it back over to a cooling coil. In essence, a cooling coil. And then the air goes through that because the supply air comes in here for the unit. We have supply air. The inlet goes through this cooling coil, 100/70, so 30-degree depression again. Leaves at 77.5. And then that water comes back to the cooling tower, pumps through there, cools off, and just recirculated through the coil again. Now, you won't lower, draw water out of this system because that coil never gets below the dew point of the air because you can't. I mean, the water is that temperature. So you won't have a wet coil like you do with a DX or chilled water, but it will lower the temperature from 100 to 77.5. That's an indirect system. Now, what does that really mean? So you got a 75% effectiveness. So 30.75 is 22.5 degrees. 100 minus that is the 77.5 we talked about. And what is that really equivalent to? Sensible cooling is 108, depends on delta P. 243,000 BTU, a 10,000 CFM unit. That's equivalent to over 20 tons of cooling we got in there without refrigeration.
That versus the cost of 20-ton refrigeration air handling unit is an amazing lot of money.
Well, operating competition.
Operating
That's good.
cost, yeah.
So if that wasn't good enough for Aztec, they wanted to go a little bit further. So they made an indirect. So it's a hybrid. So the first stage lowers the wet bulb and wet bulb, like we just talked about. The second stage now is going to lower the dry bulb using the first stage as a starting point. It goes through the indirect, then it's going to go through a direct. Thus, indirect, direct cooling. We keep it simple here. So, cooling tower, we have the air coming in, it leaves the coil at 77 degrees. Now it goes through a direct evap cooler. We're adding water to this one, so it's got wet. But we leave at 64.6 degrees. You also notice we're raising the wet bulb because we're approaching the wet bulb temperature because that temperature, we're adding water into the system. And so those are almost the same. It's a saturated air when it comes out of there. So look at that now. You can take 100 degrees and bring it down to, call it 65 degrees with an indirect direct. So let's look at the start again. Here's stage one. We've been through that. And stage two at a 0.87 effective. We dropped it up to 14.7 degrees. So, 14.7 times effective 12.8. Get it down to 64.7. 35.3 degrees total temperature drop between an indirect direct, across an indirect direct. Tonnage-wise, what's that going to give us? Look at that formula again. Without having any refrigeration in there. So that kind of touches base on what you see the name being built out there under direct, or do you see the Aztec name with the indirect or indirect direct? That's some of the things we can do with it.
Now, just to see the size, I guess, the 31, let's say, 77 tons of air, cooling air, what would that compare to building size?
Buildings. Well, that's for 10,000 CFM, so, I don't know, anybody know how many CFM exhaust fans we have out there in the welding booth, for example, that we're probably replacing?
Like 3 fans.
3 fans, well, I think they're around 3,000 a piece that we're moving. I bet you got close to 10,000 CFM going through your paint booth. So
10 of those.
it's probably replacing the air that the paint booth would exhaust out. So there you see the summary with the 31.77 tons. Now here's some other things we can do. You can also put a coil in there, the extra chill water coil. You can't run this and this together. You just have to burn up the other. But it can be, some people leave the direct section out, put the refrigeration coil in there for that extra cooling, and have more control of what they're gonna, without adding humidity to the air. You can also put a heating section on there. We can offer gas, electric, or hot water as a heat section so that you have a complete system. We've got I think it's a 5-story office building out in Denver with one of these units on it. And last I ever heard, it did a great job, pulled the whole building down, and again, no refrigeration. But that's a big unit. That thing I think was 20 tons operating weight. So, but, and that was a complete system, heat and everything. So they can be used in office buildings. One place we used to like to use the indirect section, not so much the direct, but the indirect, was in printing operations. They couldn't send humidity, the paper would stick together. So they couldn't stand humidity in the air. And they liked the dry air that's getting off of the indirect system. You can see how that would be valuable in something like that. And here's just a synopsis. If you take a direct section, it just goes right up the wet bulb line we talked about.
Yeah.
So if you're in a sort of at 100/70, and your leaving air was 73.6, it just goes right up the wet bulb line to your new operating or leaving air point. Give an indirect section, it follows the simple cooling line here. So you start out at 100.70, go down to 77.5. Straight line across there. If the indirect direct, it follows that part way, and then the direct section is up the wet bulb line again. Up by the direction of the cooling, which system. That indirect, there's your combinations. So kind of a recap of what products are coming out of this plant. We have the Alton HVAC. These are direct HVAC. They're an outdoor horizontal unit. They aren't made for curb mounting, but they're horizontal for roof mounting on a pier or platform or whatever. The air handler itself ranges from 5,000 to 64,000 CFM. And then we have the washer only. You might be shipping that out, somebody's putting on their air handler or whatever. But we can offer those modules from 4,000 to 30,000 CFM, just the washer section they can add onto their system. Our guys have worked with for many years since retired, but he was Mr. EVAP. He could still these things in his sleep. One of most popular areas he was selling them, and it was down in Atlanta and Florida. And you think it would just be opposite where they should sell them because of the humidity they get down there. But they were using them in laundries and dry cleaners primarily. So any heat generating process, welding, transformer rooms, forgings, whatever, generating the heat, you don't mind the light. It feels good regardless. He sold those down there all the time. He got a letter from a customer in Florida one time because he helped size them, lay it out, the ductwork, everything. He was great at that. And the guy wrote back and thanked him for your time and their great equipment and whatever. He goes, for the first time since I've been in business, when the girls go on break, they stay at their workstation. Because he wasn't trying to cool the complete space. He was blowing the air on the people working at the station. He didn't care what it was like over here in the bagging area where they were at their station. He kept them cool. And when they went on break, they stayed there because that was the best place to be. And that was in Florida.
Have you ever been to a laundry? They produce horribly. I mean, it's amazing.
And steam and
Steam and everything else.
they were tickled to death. So he thanked them for his great design and layouts. And again, that's the area you didn't even think they'd work, but they did a great job for it. Then we have the Aztec ASC series, indirect or indirect direct. And they're outdoor horizontal curb mounting from 1,500 to 37,500. They don't go nearly as large because they're a big unit already. We peak out at 37,000 just because of the size of the box we're talking about. But we do have some indirect gas fired heating elements you can also put on there if you more.
We just shipped out a bunch of these last month.
And Scott, there's like 8 of them going to the shop now, I think. We're
Yeah.
getting ready to, if
Yeah.
not.
We're selling ASCs or we sell HECD.
How the Aztec name came about. We brought this one in at the company in Albuquerque, New Mexico. We brought it in, I can't tell you what year. Aztec used to be AZTECH. And what it was supposed to mean was A to Z technology. And then over years, they cut it down to Aztec. And again, out in New Mexico, that still fits. But that's where the name came about. That's what they was trying to say at first. All right. Before I jump on the gas heat, any questions about that you'd like to throw out before we kind of move on? All right. We're going to talk about direct gas-fired units now. So this is what will apply to your mainstays is our direct-fired line. The burner fired directly in the airstream, like we said this morning. So 100% of the available BTUs delivered to the space because there's no fluid. And you can see if we had a ductwork here or a plenum, all the air is going through, the burner's mounted right in the center of it, goes around these plates and the burner, and that's how it fires. And this is what the flame looks like when it's firing. Now this might be a flame at high fire. The nice thing about air turn, direct fire, is it's got a high turn down ratio because it's designed to handle the variation in temperature. First thing in the morning, it might be 20 degrees temperature. Afternoon, it could be 60. You're trying to bring in the same temperature of air all day long. Well, this burner can modulate to meet that requirement throughout the day. When this is on low fire, there's a cast iron manifold across the back of that with little pores through it. It looks like the flame on your barbecue. It's about half inch to an inch long. All across there, just one nice ribbon. That's the low fire. And high fire goes out about 18 inches past these stainless steel plates. So it's designed for a high turn down capability. It's a very clean burn. We'll get into a minute later of how clean that is for the burn. And very efficient system naturally. So that 100% of the BTU goes into space, and that's true, but it's only 92% thermal efficient. Of combustion are you produce water. That's just part of it. So 8% is lost through water. You won't measure them with a thermometer.
There's a lot of water in natural gas. People don't realize that. A lot of water.
Can you remind me again what turn down means?
Oh, thank you. I sure will. Didn't even bring that up on the glossary. It's a good point. Turn down means the difference between high fire and low fire. So what we're saying then, we say 25 to 1 turn down. Low fire is 1/25 of high fire.
Good question.
It is.
So modulating doesn't have a turn down.
It does.
It does.
Modulating does. Because it modulates from high fire down to a lower level.
Mm-hmm.
Most of our burners are going to be 50% on low fire.
So if they're trying to ask on a gas fired, what's the lowest the turn down can do so that they know how far the flame's going out, you would take the 25% of whatever the highest turn down is. And that's the lowest it can be to be safe without trying to go without a flame.
If you try to go lower than that, you'll have what we call blowout after a certain point in that gas iron or cast iron burner that I'm pointing at. That it won't be a continuous flame across there because it's too low to have that one ribbon.
And it becomes dangerous, the CO2 and it.
Yeah, the air. And you'll have gas coming out yet, but it's not being burnt.
Right.
Yeah. So 25 to 1 is the number that we stick with. And let me be perfectly honest with you. That's the burner capability. The controls, we're going to limit that more than the burner does. The controls we're using, you might get a 15 to 1 turn down or whatever, to be perfectly honest. And then also, if you don't start out at high fire, I'd order a burner that is, let's say, 900,000 BTU that you ordered. But the burner got the capability going to 1100. You're not even starting out at high fire to begin with. If you're only going to get 900,000 out of it. So that means now 900,000 down to what the level is at 100 or 1,000,001, that becomes your new low fire. But this is the maximum we get out of it. Parts of combustion go right in the airstream. You saw that in the picture. With the right place it can go, it's right in the airstream, and we're blowing that into the space. And there's no fluid required, obviously, because of that.
What is that?
The stack, chimney,
Okay.
stack,
Where
whatever.
those products of speed combustion go.
Yeah, so that's a good point. Again, there's various flue, a stack, a chimney. There's not the other one I can't even think of, but that's the main thing. They all kind of interchange. Good point. So, as we said before, 90% of the heat content goes into the ratial temperature. That's why we have to use this formula. CFM delta T times 1.08 divided by 0.92. That gives you what the burner input has to be.
I'm sorry. Wait, you said, so there's no food required? Where do the products of combustion go?
In the airstream.
They stay in the airstream.
But it's so high efficiency, it's not like a heat exchanger. It's not gonna kill.
We'll show you the numbers here pretty soon, so don't get too.
Okay.
And don't get me wrong, you're not the first person, because I remember when I was in sales years ago, some guy had a unit delivered to him, and he called me up and goes, well, I got this unit, but I don't know where the chimney. And I go, well, you don't need one on this unit, it's direct fired. Huh? And he goes, I go, well, there is in the airstream, but it's safe. Not in my building. He's in a back, but but people still fight that because they just don't trust it. But
So when they have the switch on those that they order that's extra, is that part of the controls? They switch it off as soon as it's too much gas going through?
high limit switches, yes, if there's goes off in high temperature, it will have one that go off. We also have switches that turn it off if you have too high or too low of airflow.
Okay.
Because both of those factors will affect the burn and may affect your results, so that will shut down. If the airflow is too low, too high, or the temperature reaches too much, it'll shut down for safety.
Okay, so that's like at the actual controls is where that would be?
It's on the unit there, right? The air switches are right on the burner profile. Back up a second here. You'll have a couple tubes sticking through this that measure airflow. One set for high pressure, one set for low pressure. Either one of those trips will shut it down. And the high temperature is typically mounted right in the discharge of the blower. So again, 8% of the content is consumed with putting water vapor of the airstream. And the third issue, unless you let the building cool down to below wet bulb, or not wet bulb, but the dew point.
Yeah.
And then it can rain on you. So if you keep the building warm, it's fine. But we have seen buildings where they think because of energy conservation, they want to raise that to lower the night mode. They came in the morning and the rafters are just wet. This goes back to what you were getting at. This is how safe it is. What we have to meet, we're testing this standard, ANSI 83.4. And for CO2, we can't have more than 4,000 parts per million. American Society of Hygienists, or whatever it is, allow up to 5,000 parts per million in the room. So you see, we're below that number. CO is like one of the most concerning ones. You don't want carbon dioxide poisoning. ANSI says we can't add more than 5 parts per million. OSHA lets you have 50 or 25 in the room, or 5,000 is the weighted average. So you can see we're well below any of those numbers that OSHA or the hygienists recommend. Aldehydes, really can't tell you all the negative part on it, except I know it stinks. If you get an aldehyde that's high, it puts out an odor that you don't want to be around. I can't remember the real danger, but I'm sure it's there or they wouldn't limit it like it does. And then nitrogen dioxide, half a part per million. OSHA allows 5, the high units allow 3. So these are the numbers when they send our unit in to get it certified, we have to meet those numbers. So that burner, and there's a couple people that manufacture it, but it's a very safe burner design that's been used for years and years. Now this morning, I've been in the business since manufacturing side of it since 75. And they've been used for this for that many years, and they're very well accepted, and they're safe, believe me. How was this accomplished? Getting a high turn down. The first one, we have controlled aeration patterns. We'll go back to a little bit pictures later to show this better. The roll-up plates that sit around the burner to maintain the proper velocity, and it's positioned on the uniform or the uniform pattern across it. That means that we normally put it on the draw-through side. Get a lot better air pattern on the suction side than you're trying to blow through with a high velocity. So going back to this picture here again, I know you can't see it, but I can try to point it out that on these stainless steel plates on the burner, near the cast iron pipe here, it's real small, very, very tiny holes. And the reason is for a low fire, you don't need that much combustion air. That's all you need. It gets a little bit bigger in the middle, the holes increase to, I don't know, let's say, 1/4 inch, 3/8 of an inch.
Three, say 3/8.
You get to the very end, it's well over a half, because more flame, more. Past the profile plate is getting combustion air through the air itself. So by that controlled aeration pattern, the manufacturer is able to give us a good, clean burn throughout the complete thing. One of the burners we used to use here years ago, we had to stop making because they wouldn't have combustion tests at the mid-range. And they call it the mid-range blues because I think they ended up going out of business.
Yeah, they're gone.
They ended up going out of business over the years because they lost so much sales when we had to go to alternate manufacturers with it because of the performance issue. It's very well determined pattern that's been in business for years. So there's that, and then I know you can't read it, but maybe the handouts show it. This and this is marked as profile plates. And every unit that goes through engineering, they size this opening based on the size of the burner and the CFM that unit's got ordered so they can get the right velocity going through there. So every unit is custom designed by engineering to get the right velocity across that plane.
And that's why we test every unit. The test. Sure it's working.
If we don't do combustion tests, but we fire it up and make sure that, you got a good clean burn and whatever. If you start getting too little air, that thing that's open too much, you get what we call the long lazy flame. Yellow because it's still searching for combustion air. If it's a tight flame like this, you're getting the velocity you want. And it's too tight, it'll not only increase your static pressure across there because you're driving that through, but you also have some side effects from the combustion we'll get into here in just a second. And again, as I pointed out, it's on the draw through side, it's on the suction side of the blower, because that's the cleanest airflow across it, where the discharge is so turbulent at high velocity. The suction side is very even. Now, as Crystal brought up, we do have pressure switches across there because we're shooting for this optimal velocity. 4,800 to 3,200 feet per minute. That's how fast we move that air across the burner. If it's too high, we add CO. We don't want, you know how critical that is. So we add the aldehydes, which gives the odor. So again, the pressure is too high. We're going to shut the burner down until they can. It doesn't stop the unit, but it turns the burner off. If it's too low, we again add CO concentration. No good. We got NO2 that is high. As I just said, the flame length will increase because it's a long, lazy flame now trying to get more combustion air, which means it could impinge on other components downstream. If you see our units out in the shop, there is not that much different or distance between the burner and our blowers. You're coming in and getting the question, what type of fan? And when the earlier slide, what are we looking at? Thank you. Vertical fan. Air comes in here and this piece is flowing down. Going down into the space. And this is your back control living air center. So that was going to control the living air. So what do we do with this building for direct fire units? What can we offer you? We have applied air and temp right. They both make the same unit with a different name on it. DFL or CMA can be either horizontal or vertical. It's made for indoor or outdoor applications. We go from 2,000 to 16,000 CFM in those units. They're all single blowers. We go up to almost 2 million BTU input. That model. Our applied air DFM or temporary TMM. Again, we can make horizontal or vertical. This one's for indoor applications only. 1,600 to 64,000 CFM and almost 9,500 BTU. MBH, I should say, not BTU. 9,500 MBH. So you're approaching 10 million BTU there. So here's the real workhorse for, at least it was when I left. Applied air DFC or temporary TMC. Again, horizontal or vertical. This one's for outdoor applications only. 1,600 to 100,000 CFM. Almost 15 million MBHM or BTU input. And we do have cooling options available for some of these. We have evap cooling that's good all the way up to 100,000 that we can add. We have DX and chilled water that peak out about 50,000 only because the coil gets so big it's not, we can't ship it. Coil's just that big. You think at 100,000 CFM at 500 feet per minute, we'd need 200 square feet of big box. So that's your direct fire models, the things we can do with it. Hopefully it's impressive. It is a very safe unit. Like I said, because of the controls we have now and those standards we meet for the burner combustion, there's more and more applications. These are more than just makeup air units. These are also used for space heaters. They're never going to be allowed for 100% return air like a home furnace would be, but we can bring up to 80% return air, 20% outside air to help purge some of the combustions and still keep the building safe. And that is allowed by the new standards. All right. Now we're going to jump to indirect fire. So now, the burner fires into a heat exchanger or a combustion chamber, and then that heats up. That's where we transfer the heat over to the air. Combustion is then exhausted through a flue system, chimney, whatever you want to call it, like goes outside the conditioned space. So this is kind of a picture like almost a smaller residential type unit. Air coming in here, goes through a, what I'm going to call a clamshell heat exchanger, and then warm air goes out this direction, the stack or the flue goes out the other way to go leave the space. Our larger ones that we build here, air comes in the bottom, in this case being a vertical. Couple of blowers that blows across our heat exchanger. And then this arrow here would be the one we vent it outside, and this will be ducted to the space or blown in the louvers, whatever it might be. So this is the little one, this is big boy. This goes up to 6 million BTU. And our 6 million BTU unit, that's output, that's not input, that's output. This chamber alone, just that heat section, 141 inches high, 12-foot of chamber for that section only. So
That's it.
Oh, she's not.
it takes a double drop trailer just to hold that one section. Forget the rest of the components.
How big was the 104? 12? 12 feet high? The 104s, think so?
They were taller than 12 feet, I thought.
Yeah, oh, yeah, they
I
were.
bet they were.
Yeah.
I was kind of imagining
I
just.
think they were almost 16.
Oh, okay, okay. Well,
Yeah.
I was kind of imagining compare with the size of that one.
Yeah, well, they were huge. They were, no doubt about it, they were huge. So, what is an indirect? The important thing is flame never comes in contact with the airflow. That's the difference you need to remember between indirect and direct. Indirect, the airflow and the flame are in direct contact with each other. Indirect, they never touch. Flames in the chamber heats up, that's what heats the air.
If you have a gas furnace in your house, it's an indirect. There's a flue coming out and the air moves across the heat exchanger. All the combustion takes place inside the heat exchanger.
So the gas / air mixture is lighted inside a chamber, and that's isolated from the airstream. Again, they never touch. Remember that one. They combustion air, and this is drawn from outside of the burner. So if you've got the indirect fired burner sitting here in the unit, the combustion air comes from that area for that burner. So in essence, you're pulling a slight negative on a building by all the combustion air coming in. Because that's not coming from outside, it's coming from your space that goes in there for combustion air, and then that's exhausted out. So you lose that air. The products of combustion are discharged to the atmosphere. Clean burning is not nearly as critical as a direct fired system. To give you an example on that, I went out and direct fired the CO, 5 parts per million. We have to meet. Indirect fired is 400 parts per million. So that's why you don't ever want to hold in your heat exchanger, because that can get in your airspace then.
Absolutely.
So why would anyone pick the indirect? The direct is just to save.
Well, it can't be 100% return ever, so you're going to bring outside air in then, at least a little bit. Outside air is a lot more costly to heat up because it's going from outside temperature to versus what just the return temperature is. You might be returning the air at 60, throw an example, heating it up and discharging it, where if you bring in outside air in, here up north, that could be 0 degrees. That you have to heat up to a neutral condition again. So you're always going to be bringing in some. It ranges on your application, but 20% minimum that you have to bring in. And then can be used for the 100% return air applications for indirect fire. And there's no concern with products in the airstream causing health issues. So, I mean, it's just a safety. Direct fired units by standards now can be used anywhere except sleeping quarters.
So you couldn't use it in the house. Sleep or
Hotels,
hotel. Yeah.
You said that was direct fire.
that was direct fired.
Okay.
Not a direct fire. It would have to be in.
So you're saying it's not, which means it can now?
Cannot.
Oh, so it can't.
So,
That's just purely for safety.
And so in Doug's office, you can't put a direct fire because he sleeps in there.
That's right. Why that door?
And you know. So here's a typical picture of one of our smaller chambers. So the burner would mount down here, fires into this big chamber. And you have what we call two passes in the chamber because the flames shoot all the way down here, almost licks the rear wall. And then it gets pulled back, this collection box on this end. So you have a flame shooting out that way, gases pulled back into this collection box. And then you have two passes of tubes. So we have a 4-pass heat exchanger. 2 passes in the main chamber, 2 passes of tubes. And then an exhauster mounts on this mounting arrangement here. So that's how we get the 4-pass heat exchanger. The primary drum, and then the secondary tubes that we just heard. I think I've got, yeah, here it is. The drum is the primary chamber. We get about 60% of the heat released in that drum itself, the main drum. You get a good. That drum's always a 400 series stainless steel. It's made for that temperature. It's 409 or 4, I think it's 430. So it can take easy. And that's another thing we have to do when we get them certified. We have to make sure the temperature of the steel is only 75% what they call the scaling temperature. When the metal gets hot enough it's scaled, we have to be 25% less than that. So again, 2 passes in the drum. And we go right there. You do not exceed 75% of the scaling temperature of the stainless steel. And again, we like to brag about that, but all people have to meet the standards. That's just the way it is. So then we have the secondary tube. The other 40% of the heat is released through those tubes. We have mild steel as standard, which is just a mild steel tube. We can offer stainless. And stainless would typically be offered when you have 100% outside air and you're going to have temperatures where it's going to condense inside the tube. You don't want that. Where you got real high turn downs and the combustion products could start condensing before they get exhausted. So in those cases, we might recommend stainless, but as a rule for just the return air application, space heating, mild steel works great. And we give a 10-year warranty on that the way it is. So can't complain about that. But again, you got 2 passes of tubes. It's going to give you the 4-pass total design. And a lot of you haven't seen it. I'm sure Crystal has. The specs come in, they say 4-pass heat exchanger. That's what we're getting at right there. And there's no internal restrictions in the tubes or baffles like some people we used to do to get the efficiency up. They tried to slow the combustion products down to the tubes to get more heat transfer. And that were good in the ideal situation. I know, especially when we had oil units, they would get stood up so bad they'd have to get taken out and cleaned about every year because they would stood up so bad. And we've seen another unit, I remember came in, they were upset with it because it wasn't working. It was a propane unit, but they had the combustion air sent home and it stood up. And we had like 4-inch tubes. You couldn't get a pencil through here. The soot was so thick in it.
Chunk of coal.
Solid coil or coal, the complete length of those tubes.
Wow.
So we don't have anything here that has internal restrictions to restrict that. And we're still able to hold the 80%. It's what the other manufacturers are doing as well. Here's our range. Wide air IF or the temp-right DIN. You make them either horizontal or vertical. That's for indoor applications. 3,500, 94,000 CFM. And you see there from 350,000 to 6 million BTU output. That's keyword there, output. That means at 80% efficiency, your input's like over 7 million. Pretty good sized burner. The IFW or the TIW is the same thing with a weather house on it. So it's an outdoor model. with no curb mounting, but the same arrangement, same CFM range, same BTU range. It's just got a weather house for mounted outdoors. Then if we do have an application for curb mounting, we have the IFR or the temp right PIR. That's horizontal only. It's curb mounted. 2,300 to 53,000 CFM, and from 250,000 to 4 million BTU output. So that's the range of products we can offer on the indirect fire. And again, the key thing to remember, direct air flame in the air come in contact,
Oh, they do come.
direct fire,
That's direct.
Hmm.
Indirect, they do not.
correct.
Thank you. Just want to make sure I understood it correctly.
There's a chamber there, so they don't touch each other.
Okay.
Stupid question there.
No such thing.
What is the difference between the MBH and the BPU? I always get those mixed up.
M means 1,000.
Yeah.
So if you have an MBH, it's 1,000 BTU.
Okay, but it's the same, you're measuring the same thing.
MBH is 1,000 BTU per hour. Yeah, that's the rating, so. All right,
Now
now,
we'll still build a three-phase burn off for each area.
yes, on the IJ series. We're gonna touch the IJ. I don't know if I touched upon the 3-pass. We do mention the product at least on this series. Here's one of the more popular units here in Dallas, at least I'm assuming it still is. The method continuously circulating large volumes of air, but at the floor level, we condition it. And forcing it out sideways at level above the occupied zone. So, graphic here, almost yet, we'll get to it. It's typically 100% of circulation of room air several times per hour. That's what we need to apply. They're tempered slightly by heating and cooling, and I say slightly, that's an important thing. The indirect fired unit, where it's a ducted system, we might heat that air up to, I don't know, a delta T of 80 degrees, for example, 80, 85 degrees. And we're pushing the air where we want it. On the air turnover, we like to heat that air only about a 40-degree rise, because the hotter it is, the more wants to stay up there on the roof. We temper it, but we don't superheat it. So we can easily bring it down and recirculate it. And the same thing for cooling. Quite often the design is you want a 20-degree drop across the coil. We're probably closer to 15-degree drop instead of 20, is because cold air is hard to move. A little bit warmer helps us move that air around the room easier, so that it doesn't sink so fast. So that's an important term to remember, that we slightly heat it or slightly cool it. It's direct current, directly into the space, no ductwork, and it's well above the occupied zone. Because of the low delta T, we have large volumes of air, and this is our formula again, but now we're using, so 0.92 like we used on direct fired, now it's a 0.8, because 80% efficient on the heaters. Here. Here's the unit. And again, you see it, air is being drawn into the unit to the bottom. Condition it, that comes out near the top, blows all through the racks and whatever, clear to the end of the building, it drops as it cools, and it comes back to the space again.
So you've got a vertical unit right there. And it's blowing through those racks. Air will be stratified above that unit. But it's blowing through the racks and where you need the cooling, and then.
Well, yeah, cooling, yes.
then
Heating,
comes back.
well, heating is not stratified.
Heating's not stratified, because heating, right.
Right. That's right. So we bring it in at 70, and you might have 72 degrees at the ceiling because of our air turnover approach, and we're getting rid of the stratification. We had a circular pattern going.
And that's why that fan runs continuous, whether the burner's cycling on and off, but that fan is always turning.
That's right.
What does it mean by occupied zone?
Well, that's basically what we're talking about for the creature level down here where the workers might be. Is the, 6 feet high. I wish I could say that for me, but 6 feet is the electrified height. So yeah, we're just talking about where the people are gonna be.
Those do work pretty well, because I got one over there in Cool Shop. There, that thing kicked on in the wintertime. It's nice.
It really is. It's amazing what they're able to do. And we get into, well, let's tell you now. I mean, I was told many years ago when I started, my boss at that point was an air turnover fanatic. I mean, every application you could think of, oh, it's an air turnover unit, that's an air turnover unit. And he had all the rules and he gave me how to size them, whatever, and I was automatically doing it. And I got to go out to a trade show, one of the reps in the Midwest. And he said, oh, while you're here, I got a unit I want to show you. We just got it installed. We walked in the building like down here, and there was nothing else in it yet. The unit had just been installed, no racks or anything. And I looked down into the building. It looked like 3 football fields away. There was one unit sitting down there. It looked like the postage stamp to me. It's all the bigger it looked in that unit. And I stopped dead in my tracks. I said, my gosh, what did I do wrong? This can't be right. And oh yeah, don't worry about this. And every time I saw his number come up on the phone, I had a heart attack for about 3 weeks. But the system worked great. I mean, you apply the airflows we're talking about and the temperature they need for their weather conditions. As you say, they do a great job.
Air will blow until something stops.
So what's the limitations to these? Well, they're designed for large industrial or warehouse open areas. That's the key word, open areas. We're working in an office because we're moving air throughout the whole space. So they're open areas that we need to try to condition. Intended for 4-level installation, and out of the 4, because that's where you're trying to pick the air up at. Not suitable for corrosive or wattle environments because you don't want that going across the heart chamber. And it's primarily designed for indoor installation, and I say that legacy product. Even these, as Crystal knows, we sell all of them with an ad for outdoor application. They do come up more and more. The new Matto unit they're building is outdoor as a standard feature. So it's being accepted more and more. People don't want to give up the floor space, especially in a warehouse. That's dollars for them. So they want to put them outdoors if they can. And we just have to duct to it and then duct back into it so we can get the airflow that we need through the system and then throughout the whole building. But, so they're primarily indoor, but we do see people want to put them outdoors just because of the critical floor space they don't want to spare. So here is a picture of one of our air turnover units. This is the IFB. That's one of the big units that we sell on air turnover side. It's heating only. You ever see them built out there? It's a very small angle iron framework. The 4-passage exchanger we've talked about. 2 pass through the main drum, 2 passes the tubes. It's a power burner for 2-stage moduling operation. This exhaust fan here is direct drive with no belts to worry about. And we have the energy efficient propeller fans. Again, they move large volumes of air, but they don't handle the static. So as long as we don't have any cooling coils, whatever on here, they can handle that static. Now let's go back to this morning's session. We talked about standard air. And it was, what's the weight of standard air? Can you remember that number?
I'm sorry.
The weight of standard air. I give you a weight per cubic foot. They were all asleep.
Yeah.
Standard air weighs 0.075 per cubic foot. at 0.75 pounds per cubic feet. Okay, 0.75. That's again based on standard air at sea level, all these
Yes.
conditions.
Yes.
There you go. Now, that's a small number, right? This unit here, the largest model is 150,000 CFM. You would have 3 fans versus the 2 shown with 150,000 CFM. Put that in perspective. 11,000, 150,000 CFM on 0.075, 11,250 pounds of air per minute we're moving.
Hmm.
Now you know where the horsepower comes into play.
Right.
Over 11,000 pounds of air every minute is going through that unit.
You don't think of air having a weight.
Right. Right.
And if well, it'll always be indoors, but if you had a unit up in the Arctic Circle, cold air weighs a lot more.
Because it's denser due to the cold.
So just want to throw that out to get a relationship, that's a small number, but think about it.
Right.
Time we have.
Yeah,
Sections, I guess. It's all good though.
blame me.
Well, we're in.
I'll take it. I'm the printer.
Keeping us on our toes.
Pay attention.
So we had just a straight heating unit for years and years, and it's still a success because people are more and more moving to cooling. People want it because of the working conditions, or their product have to have cooling so they don't go bad on there. So we've come up with the ISA or TAA for heating and cooling applications, or cooling only, whether it might be the same angle iron construction, same heat exchanger. So with the angle iron, it's a 4-pass design, all that doesn't change from the other one, or the IS series in general. We use high velocity discharge grills up here on the top because I need to back up, I didn't clarify that. On this particular heating, we just use screened outlets. We're not trying to throw the air, we're trying to just get it out there and it just kind of wafts through when it goes up the ceiling. But on the cooling model, we have high velocity grill because we do need to push a burner. It's down, we need to push it across there. Now, as Doug said, the nice thing to remember about cooling is the air will not go any higher. It's going to stay at this level or start dropping eventually. So you don't have to worry about the space above that. That's a thermal zone for you. But so we have those to help push the air. As I said before, it's the same heat exchanger and burner as the heating series. This coil can be either DX or chilled water. And then we use heavy duty centrifugal blowers because the pumps don't work here with the heater, the cooling coil. Another thing we do is as the cooling coil, we're going to have filters on it. We're going to keep the coil as clean as we can. Between the filters, the heat exchanger, and the coil, and we're talking centrifugal fans versus axial fans because of the static. In this particular case, you see we have 3 fans, but they're all yeah. So we just one blower motor to control those. Right now, one point this I see this is kind of our this little Bible, but it's just a little thing. We have a factor on first of all, building a new building, tighter construction. You don't need as much air as you do for the older building with loose window panes, single pane glass, all that, poor insulation. Here they show roof of R4, here it's R15, and that's not even the newer current ratings anymore.
Yeah.
But it's just the difference. Look, you get an older building, 60-degree differential, you need to move 2.75 to 3.25 turns per hour. So you take the complete building volume And you divide it out down to a minute, how many airflows you need to get, we'll use it on term of 3 turns per hour. But up here, you only need 1.75.
So you're gonna turn that air completely over in that period of time.
That's right.
4 passes every time.
Through the heat exchanger. 4 passes across the heat exchanger, but not the air terminal.
Not the airflow.
Okay.
But at the heating unit now. Well, it's a whole new ball game. Again, cooling or cold air is harder to move. Now we're talking up to 5 turns an hour. Here's the good news. Doug and I have said on heating, air rises, hot air rises. So we have to figure the volume from the floor to the ceiling. On cooling, you figure the volume from the floor to the top of the unit. So that'll help get this 5 turns per hour. So here's some of the products we offer here. IFT. Heating oil. Use the axial prop fans. We go from 6,600 to 150,000 CFM. That's the example I gave you for the weight of air. Up to 150,000. And that again goes up to 6 million BTU output. The IFA or TAA at heating and cooling or cooling only, 13,000 to 81,000 CFM, 750 to 6 million BTU output. Something we didn't talk about, we also have the CAT or the THC unit. That's again because the reps wanted more, trying to do more with less energy. So we have a special prop fans that do cooling only. They can't do cooling and heating, but they do cooling only. We go from 13,000 to 81,000 using those axial prop fans. And we have the same tons as what the other one can offer. The IFJ, that's what Doug mentioned a little bit ago. I think that's what you have in the coil shop you just talked about. It's an IFJ series. That would be a smaller 3-pass heat exchanger. Heating and cooling for the smaller spaces. It's not made for the large warehouses. It's more like an auto garage or something that they're designed for. They go from 37,000 CFM up to 670,000 output. We have also the IFS or TAS. This is more what we call a support unit. There's no heat in it per se. And first of all, you might have a building, we've had these before, where let's say they've got a dozen unit heaters in there, Stirling gas-fired unit heaters, perfect example. They're putting heat in the space, but they can't get the air down the floor. It's all rising up and not going down there. Put an IFS in there, just as the air turnover approach only, move the air. It solves the problem. Their heaters work great then, it gets out through a complete space. That's also, like I say, it's a 4 unit that you need to move the air, but we can also put all the heat sources in there, electric, steam, hot water. So if you don't need gas heat, we can use the IFF and put all the heat sources in there. All right, we're going to touch on some EX systems. First thing you want to kind of point out is you need to understand the effective pressure on the boiling point and condition point of a gas or liquid. And this shows the boiling point of water. So we all know that atmospheric pressure is 14.7, so just over 10. And it's 212 degrees, water's going to boil. Now, I saw this firsthand, so I know if you start bringing this unit into a vacuum, I've seen water boil at 100 degrees because it's in a partial vacuum. On the other extreme, if you start getting 100 pounds of pressure, you have to 330 degrees before it's going to boil. So Refrigerant gases are the same way. At low pressure, they're going to boil off faster. At high pressures, they're going to accept more heat. So that's part of the principle. We go condensing unit, that's high pressure. So it's going to release the heat at that higher temperature then. Then it goes through a system we're going to get through here in a second. It puts into a low pressure. It's going to boil off faster and pick up the heat in your space that you're trying to get rid of. But the important thing to remember is higher the pressure, higher the boiling point. Or lower the pressure, lower the boiling point. So again, if you have a high pressure, and I wish this scale would jump from 10 to 100, I wish it'd be more in between, but it will jump up as the temperature, as the pressure increases. That's the thing they need to know. And refrigerant gases work the same way. So here is a typical refrigeration cycle. See the high pressure vapor, it goes through the condenser. We know we have outside air going into it. This discharges hot air. And now leaves a high pressure liquid. Goes to what we call a metering device. I'll show this in a minute. It goes to a low pressure then. The liquid or vapor that might flash off. Goes with the cooling coil, indoor air, send it out. Hopefully it's cool air. Now it's a low pressure vapor as it comes out of there because it was a liquid. Now it's going to be a vapor as it boils off. Both back to the compressor. The circuit starts over again. That's your refrigeration cycle in general.
And the refrigerant changes states is kind of the key there.
And so as we learned this morning in the latent heat, when it changes state, there's a large BTU differential there that you take advantage of. So here's what a typical compressor looks like. That would be inside your connecting section outside. So that's again, it pumps the refrigerant through there. So our refrigeration cycle, we're looking at here. This is now the heart of the system. Again, it's what pumps the refrigerant through. Then once it leaves there, what outside is going to look like.
Mhm.
Compressor down here below, the bottom port, you have a connecting fan here. It's going to exhaust the heat. Here's the metering device we mentioned. This is the metering bulb on the coil that controls the flow going through it. If this changes, it goes from the high pressure liquid that controls how much comes out to a low pressure liquid / vapor to get the cooling effect that we need. It's a real small orifice, so as that goes through there, it goes to a lower pressure, and that's where it. And you have a cooling coil. This is a typical DX coil. You see the air handler or whatever. This is a coil. The air's going to come around. Goes through that. It comes a low pressure vapor again as it boils off, and go back to the compressor. Now, because I had one down in my neighborhood, milder climates, they can use heat pumps. And a heat pump is a refrigeration system like we just talked about, but it's got a reversing valve in there. What does the reversing valve do? It flip-flops the condenser and the evaporator. So now you get that reversing valve for the heat mode. What used to be the evaporator is now the condenser in your ductwork in your house or whatever it might be. So it rejects the heat into your house instead of outside. The cold air is then rejected outside. That's all that's doing. This reversing valve takes your system and flip-flops it.
I have a heat pump system in mine. And if you're ever around a residential condensing unit in air conditioning mode, you put your hand over that air that's coming out of it, and it's hot, and it's getting rid of that coil, but when you flip that, or when you turn on the reversing valve, now it's blowing that heat through the evaporator coil inside your house.
And you feel cold air outside come out of it.
Yeah, very much so.
And as long as the air is above absolute zero, they still work. They aren't nearly as effective in a real low temperature, but they do reject heat. That's the important thing. Simple concept. I mean, the roof will come to the- but the roof has components, they have the ability to- Hello? This time.
Oh, wow.
Well, I gotta go sometime.
Oh, yeah.
I'm talking about 15 minutes,
Somewhere around
about
here.
15 minutes.
Yes, I do.
Yes, please.
I have, I find the right folder.
I think so.
Man, 2 flunks in one day, can't take that.
Feel like you're back in college? Cool.
Back then, we used to have fun.
So,
Close that was the deal. And then there, and then we'll-
hard.
All right, again, as we had this morning, if everyone's ready for it, it's gonna be a 10-minute time frame on this, but that's the permit that Rich gave us. Open book, the 10 minutes limit.
Open book.
Yeah,
Yeah.
open.
Got your notes.
Oh, no.
No.
Oh, that changes everything.
But again, 10 minutes.
You better know what you're looking for.
Be able to use any notes, the handouts, whatever you want to use.
Special for you.
Yeah, thank you. The answer already?
No,
Oh.
that's why it's special.
Oh, okay.
All right, I'm gonna start with.
One moment.
Fair enough.